What we're doing is a creative process. So we definitely search for those times or those occasions where you can make your code feel a little bit like art.
New frameworks, new standards. Things are changing so fast. You're always learning. That makes me happy.
For me, it was really fascinating when I discovered what programming actually is. When you make up an algorithm in your mind, you could execute it yourself with pen and paper or just by thinking hard. This is truly exciting.
It's really creative. Once you get the hang of it, you can create so many different ideas. It's really impacting the real world.
Every software is an artistic project. Since the first day I saw a line of code, I fell in love with Java programming. It's something on which I love so much.
I'm not sure if I've lost myself in coding or it's who I've always been. Coding definitely is going to get you once you type your first successful LOL. You can do and undo whatever you want, and makes me want to do more. Obviously, I sleep less, I code more, and I'm delighted when every time my customers say they're happy.
It's a very creative activity. If you ask an artist or a singer, why do you sing, or a musician, why do you write music? For me, I'm an artist, I'm a musician of my profession.
One way of looking at it is that code is another form of communication. With Sonic Pi, the goal is to explore the potential for code with music. Can we get anybody, not just musicians, everybody making some kind of crazy beats and sounds by writing simple lines of code?
Once you get your code run, the feeling is awesome. You can achieve anything within your imaginary with coding.
That's why I wanted to code in the first place. Create something brand new that hasn't been seen before.
Having imagination to build something beautiful and efficient, beautiful and usable. It's freedom.
Please welcome Greg Pavlik.
All right, hello, welcome to Code One. I'm excited to be here. My name is Greg Pavlik, so I'm a Senior Vice President here at Oracle. I'm responsible for our data management, artificial intelligence, and developer services on our Oracle Cloud infrastructure. We got a number of great speakers today for the keynote, so it's going to be a great series of talks. So first up is Dr. Kirk Borne. He's a principal data scientist with Booz Allen Hamilton, where he focuses on the application of data science and machine learning to a variety of disciplines. Works across industries. Previously, Kirk was a professor of astrophysics and computational sciences at George Mason University. And since 2013, he's been one of the most recognized influencers on social media around big data and data science, digital tech overall in the industry. So Kirk today is going to discuss data science at the intersection of emerging technologies. He's going to show us how you go from data to insights to action to value. So without further ado, let me invite Dr. Kirk Borne up on the stage to join us.
Twitter fans in the crowd, thank you so much. Hello, OOW19, hashtag OOW19. So glad to be here, so glad for this opportunity. Thank you, Oracle, thank you, Code One, thank you all for being here this afternoon. So I'm going to talk about this topic, which is near and dear to my heart. It's a four-letter word, and I use this four-letter word often, so I hope it doesn't offend you. The word is data. I talk about data a lot in my life. I use data a lot in my life. But see where this starts. 49 years ago, imagine 49 years ago, oh my gosh, I can't even think that far back, but imagine 49 years ago, a 15-year-old high school kid who had a vision and a dream to become an astronomer, an astrophysicist, ran across a book that was basically just tables and tables of tabulated data. Data giving the positions of the stars, the planets, the moons around the planets, the sun, the moon, all these things, eclipses, all these events, all tabulated when and where and how. And there was equations in the back of this book explaining how they derived these numbers. Well, I was just probably my first real experience with data, like there's hundreds of pages of numbers as a person who loved numbers and math to begin with. Seeing all these numbers, seeing this data as sort of the basis of science was really inspiring to me. But then to see there were mathematical equations that were related to this, i.e. there were models related to that data. And crazy enough, my high school at that time, 1970, yes, that's how old I am, got a connection with a 110 baud modem to the local university computer, where we actually learned Fortran, and I learned how to code those equations, and for the first time in my life, I knew exactly the path that I was on. It was science, it was math, it was data, it was coding. And it hasn't really diverged much from that in 49 years. Now, yes, I've had a few jobs along the way. I worked with the Hubble Space Telescope. I was the archive project scientist for the Hubble Space Telescope at Johns Hopkins University for 10 years. I worked at NASA as a contract manager, managing the astrophysics data system for 10 years. I was professor of astrophysics and computational science, as mentioned, at George Mason University for 12 years. But guess what? During all those 12 years as professor of astrophysics, I never taught an astrophysics course. I taught data science. We started the world's first undergraduate data science degree program 13 years ago, because the reason I left NASA and the reason we did that program is because it already became clear to me after 2 decades working at NASA with data, both as my day job and my night job as an astronomer, could see that data was not just growing astronomically in the sciences, but everywhere else in the world. And it became really clear that data was going to be the basis for every job, every profession. Every person needed to have some kind of aptitude, skill, or literacy around data. And I said, so I decided to leave my NASA position. I'll go to the university, and we formed this data science degree program to actually teach the next generation how to use data, what is data. And it was within a computational science program where we taught coding along with that. So along the way, more and more of my world diverged. I started getting invitations to speak at conferences about things I knew very little about, like healthcare conferences, national security conferences, smart energy grid conferences around the world. And I said, what do I know about this stuff? I'm an astrophysicist, but I know data, and I know science, and I know modeling. And so it's your gateway to all kinds of different interesting opportunities in life. And so the emerging technologies I'm going to mention today, and the amount of time I have, I can't talk too much about any one of them individually, but at the core of all of those things is that 4-letter word, data. So we're going to talk about that today, but in the context of this revolution that's going on right now. So you're probably familiar with this term, if not, I hope you will be now, and that is we are living through this 4th industrial revolution. Okay, so the earliest industrial revolution over 200 years ago, based upon steam-powered engines. Okay, and then electricity came along about 100 years later, and then of course the computer internet age, which we've all been part of, most of us, for the last several years. And now it's really different. It's a different thing. It's not just about computing and internet. It's about the hyperconnectivity between everything, all things. And what's connecting them is not just networks, but the flows of data and information that's shared to and from those things. Data that's produced by, informed by, driven by, the fuel for all these different technologies. So this 4th industrial revolution is truly changing work, future of work, careers, jobs, everything. So one thing that's interesting about this chart here is if we sort of think about sort of what's really changing in the workforce, the best sort of singular example that you can trace back 200 plus years of a profession, and that's farming. So at the beginning of the first industrial revolution in the 1780s, 90% of the US population workforce, 90% of the workforce were farmers. 90%. 100 years later, at the start of the electricity boom, the second industrial revolution, about 50% of the US population was farmers. At the start of the computer age, in the last 50 years or so, 5% of the US population was farmers, and now less than 0.5% of the US population workforce are farmers. Less than 0.5% of the population who are now feeding 10 times more people than they were 200 years ago are doing the job that was the dominant position 200 years ago. And so every industrial age brings a transformation not only of the technologies, but the work we do. So a really interesting stat came from the World Economic Forum, yes, WEF, World Economic Forum. They gave a few numbers about the changing workforce, and some of the negative naysayers, and I'm a more of a positive spin person, the negative naysayers picked up one number in that report and said, wow, look at this. 75 million jobs will be lost as a result of AI and automation and these emerging technologies within the next 5 years. 75 million jobs will be lost. Isn't that terrible? But the very next sentence said 133 million new jobs will be created. And I can do arithmetic. That's 58 million new positions that need to be filled. Assuming we can translate the 75 million to those other positions, which is just something I'm working on in a project I'm calling Career Relevance, because data and coding give you both career relevance and job security. We heard in the earlier little video clip there, once you do that first line of code and see the results, you're addicted. Same thing with data science. I've done a lot of data science hackathons, and as soon as people see they can do stuff with those things called smartphones that are in their pockets already, every kid who entered my science class who declared to me they hated math and science became a lover of math and science after that class, because they saw the power of what they can do. So we're really in this age, not just of an industrial revolution, but an innovation revolution, innovating new jobs, and innovation of new work, innovation of new opportunities, and many of these opportunities, like I said, 58 million new ones that we have to figure out how we're going to find the people to do that. So this internet thing has been around a while, and I like to tell people, well, the internet used to be a thing, so now with the Internet of Things, what I like to say is things are now the internet. Okay, everything is on the internet. Of course, in the very early days of internet, people remember those days? People put their coffee on the internet. Anybody remember that? Thank you for waving. Yes. People actually put their coffee, a webcam in their coffee room to see how much coffee was in the urn. Okay, but literally we're putting sensors on everything, so things are now the internet. And I like to say that the value of this is not even sort of the obvious value, which is all the data being produced by and used by all these things, but it's the context that those sensors give us about the world. Because all those data streams are coming from something that's taking place at a place and a time, in a context, at a location. So all this information gives you contextual knowledge about what's going on in that environment at that place where that sensor is. So literally, we're talking about the age of context now. Actually, there's a book on that right there on the screen. Okay, and another book I found recently, Outside Insight, how you can use these external data sources to even do better with all of the data you have. It's context everywhere, literally, to infinity and beyond. So who are we? So we're here today at Code One, in this beautiful place. We're digital technology professionals entrusted with this data. We're entrusted with these digital assets from our firms, our businesses, organizations, our clients, whomever we're working with. And our mission through all this simply is to discover and deliver value from these data assets. Because as this guy said, without data, you're just another person with an opinion, right? So this is how I set our mission, to discover and deliver value from data assets. It's a slightly shorter version of what Larry Ellison said yesterday. But I wrote my slides before he said this yesterday, so I think we're in sync here. He said that our mission, speaking of Oracle, our mission is to help people see data in new ways, discover insights, and unlock endless opportunities. So I'm here to talk about seeing your data in new ways and discover insights. And some of those new technologies, which I'll mention briefly, you'll see a bunch of them fly by in the remaining minutes here. Those will be chances for us to unlock these endless opportunities. So this is an eye chart. Don't try to read everything on that slide. But I just call this my expanding frontier of emerging technology. So if you could read all this, you would see things like AI, 5G, drones, robotics, deep learning, virtual assistants, machine learning, virtual reality, augmented reality, and on it goes, okay? All getting down towards the bottom, we get autonomous vehicles, quantum computing, computer vision, digital twins, blockchain. So we got this expanding frontier of new emerging technologies. Some been around for a while, some yet to come, like quantum computing. But I like to say a lot of these things, probably, I wouldn't say necessarily 100%, but probably 99% of these things are inspired by data, informed by data. That is, it's the fuel that comes in. It's enabled by data, and it allows us to create value from data. So what do we do with all the data we're collecting, which is an enormous quantity? Our mission, again, is to create value from all of that. So value is achieved when you take that data and get something out of it, a decision, an action, a product. Okay, that's where you get value, not just holding the data. In the early days of the big data hype revolution, which is like almost 7 years ago now, maybe more than 7 years ago now, the start of the big data hype revolution, people would go to conferences and brag about how much big data they have. All right, and then I would get up and speak, and I would talk about this Excel spreadsheet that I had with 26 columns and a couple thousand rows. And they said, well, that's not big data. I said, yes, but there's 26 factorial ways that my students were investigating the relationships between those 3,000 galaxies and these 26 physical parameters. And if my students spent 1 second on each one of those 26 factorial combinations, evaluating it for principal components and clustering analysis and outliers and all kinds of things, if they spent 1 second per combination of those, it would take them 10 to the 9 lifetimes of the universe to analyze all of that data. So even a simple little spreadsheet can be big data. Okay? So it's not about volume, it's about the big value you can extract from it. So there's sort of 3 broad categories of discovery from data, that is data science and AI applications that we use data for. Image understanding, language understanding, and next best action understanding or decision making. And as you might see there, a lot of these words have sort of an anthropomorphic meaning to them. And not too surprisingly, because when we're training our AI, when we're collecting data, we are emulating exactly what the eyes, the ears, the brain, everything that we have is already doing. It's receiving sensory inputs from our world and making decisions about next best action, next best thing to do from that input. And that's what we're trying to achieve here, is that cognitive power in our autonomous systems that we already naturally have as human beings. So those 3 broad categories are how we bring data to action. So it's really about connecting the dots, all right? So data itself, just bunches of ones and zeros, but when we start seeing those relationships, so we start examining those combinations of the data where cool things happen. Okay, so people who bought that book also like this book. People who watched that movie also like this movie. We know about recommender engines. It's about connecting the dots in that space of data to make decisions and take actions and deliver value. Okay, so there's a very large company out there in the world, one of the largest companies in the world, who has recommender engines. You probably know them by a name. That particular company, nearly $1 trillion business, a full 30% from what I've been reading, full 30% of the revenue of that $1 trillion business is from their recommender engine. Think about that for a second. 30% of the revenue of $1 trillion business comes from a machine learning algorithm. Yeah, wow. I can read your lips. That's taking data to insights to action. Okay, so AI to me is not artificial intelligence, and I have a slide about this later on. There's nothing artificial about it. It's really augmented intelligence, accelerated intelligence, actionable intelligence. It's all these things that give us value from our data. So really what I'm saying is about look at the connectivity. And remember, again, the 4th industrial revolution is about that hyper-connectivity. The connectivity, not only in our data sets, but even among the technologies. And that's really what I'm looking at today, is that when we start bringing together 5G and AI and IoT and autonomous vehicles and digital twins and blockchain and whatever, we start bringing these things together, we start building new and interesting products that no one ever imagined before. And if there was 26 things on my list of emerging technologies earlier, and I think there was about 26, there's 26 factorial ways to combine them. And if you spend 1 second combining each one of those and create a product for your company, you'll have a new product every second for the next 10 to the 9 lifetimes of the universe. So get busy, folks. Okay. But Leonardo da Vinci said it best several centuries ago. He said, learn how to see, because how we see is we not just see tunnel vision, we see the context around it. Okay, we realize that everything is connected to everything else. And so it's starting to find the connections between those technologies and those data sets and all those different combinations that will start delivering the value and newer and more innovative ways than ever before. So yeah, autonomous vehicles are great, blockchain is great, 5G is great, all kinds of things are great, augmented reality, virtual reality, drones, you name it, all kinds of cool things. But imagine you start combining those things in different ways, what kind of products you can generate. So the number of combinations and interactions in this graph is really big. As the little intelligent student says there, how big? Very big. It's a combinatorial explosion. So people talk about the exponential growth of stuff. Well, I got 3 curves on this, what I call my holy shoot graph. I think you read the axis there. It's my holy shoot graph. There's a linear growth curve, which is like 2 times x. There's an exponential growth curve, which is like 2 to the x power. And there's a combinatorial growth curve, which is like x to the x. That's quite a bit faster than the other ones. So when people say things are growing exponentially, said, Dad, that slowly? That's pretty slow, actually. Combinatorial growth is blowing away everything. All right. So what kind of things are we talking about here? Okay, let's cut to the chase here. Okay, I put discovery from data, that is data science, in sort of 4 broad categories. I mean, it doesn't capture everything, but sort of 4 broad categories. So we got class discovery, that is discovering the segments, the clusters in the population, subpopulation, subsegments. Okay, so that diagram in the upper left, where you see data clouds DC 1, 2, and 3, data clusters 1, 2, and 3, in a 3-dimensional parameter space, P1, P2, P3. That's just made-up synthetic data just to illustrate clusters. So we got 3 clusters, dominant clusters in there, and there we see a few more. All right, so in class discovery, not only discovered the dominant classes, but we just start discovering as we add more data, the value of adding more data here, we start seeing other clusters emerge, other segments in our population. So these might be populations of clusters. They may be segments of behavior of a machine. They may be segments of the pathway of a medical diagnosis or a drug treatment. Okay, so all these clusters are segments of some population. And as you add more data, you start discovering more of those segments. But the most interesting thing about this, what you discover here also to me is you learn the boundaries that separate them. All right, what makes Data Cloud 2 different from Data Cloud 3? So if Data Cloud 2 is a certain diagnosis for a disease given a set of diagnostic measurements, P1, P2, P3, if you have been diagnosed with diagnosis 2, and your lab results put you right near the boundary of Data Cloud 2 and Data Cloud 3, that is diagnosis 2 and diagnosis 3, if your lab results put you real close to that boundary, you know you have a very strong chance of a false positive or a false negative, because you're very close to a boundary to a new class. But if you're smack dab in the middle of Data Cloud 1, that is diagnosis 1, you can probably be fairly certain that's what it is. Okay, so learning not only the segments of the population, but what distinguishes them is the real beautiful power of all this data. So class discovery is one thing. And oh, by the way, my astronomy friends like to call this the banana diagram because Data Cloud 2 looks like a banana. All right, but I just like to call it the peanut, banana, and potato diagram personally. Anyway, so the second thing we can do with our data is correlation discovery. All right, so that's sometimes called predictive power discovery. When you see X correlates with Y, okay, then X becomes a surrogate for Y. So given X, we can figure out what Y will be. Okay, that's predictive analytics. That's predictive power discovery. But as we add more dimensions beyond X and Y, so X and Y are 2 dimensions, if we start adding more dimensions, you start getting insights. Well, that's good. We have a 3-dimensional plot here, so I got more than 2 dimensions. Good. Okay. So the 3rd dimension starts giving you insight. That is, we see this Data Cloud 2, for example. It has a certain slope in that correlation in Data Cloud 2 between parameters 1 and 3. And that slope, that correlation, strengthens at a certain place. It's a weak correlation, then it becomes a stronger correlation at some point later on. Well, if you just have parameters 1 and 3, and you just see that it changes at a certain point, you really don't have any sort of causal information. You don't have any contextual information. Remember the internet context, remember? We don't have any contextual information as to why it's happening at that point, in that elbow. Why is it changing there? I can tell you that it is changing there. I can build a predictive model and say it'll change there, but I don't understand why. But if we start looking at our other data sources, hopefully other data sources will give us some contextual information and maybe even some causal information. For example, P2 might be a variable, a feature in your data set over which you have some control. Okay, it might be a marketing campaign, a discount on a product. It might be the temperature setting on an engine. It might be something you have control over. So even though you might predict a certain thing is going to change, if you can adjust that parameter, you know that you can move the P3 response function in any direction you want, further down or further up. That now becomes prescriptive power discovery. So correlation analysis can lead to causality discovery if you have multiple dimensions, some of which are causal variables, that is, conditions under which you have some control. So predictive maintenance on engines, for example, is a great example of applying AI and machine learning to manufacturing or machines or jet aircraft engines or whatever, which it's nice to know since I'm flying home this evening. They do these predictive maintenance on the engines. And if you predict that the engine is going to fail at 2 o'clock tomorrow morning en route from San Francisco to Baltimore, I'm going to be kind of unhappy that they didn't take that plane out of service. Okay, so just like if your doctor says, well, I diagnosed you with cancer and you're going to die tomorrow, have a nice day, I'll send you my bill, well, you're going to say, wait a minute, can't you do something, doctor? Can't you do something? Oh, yeah, I can give you a prescription. So prescriptive maintenance, prescriptive analytics, prescriptions are about doing that thing that you know based upon your data, clinical studies in the case of medicine, but in the case of our data systems, finding those contextual causal variables. What can I do to change the outcome? I want a better outcome. I want a different outcome. So predictive modeling says, given X, find Y. Okay, I see a correlation of X versus Y. Given an X, I can tell you why. Prescriptive analytics is the exact opposite. Given Y, find X. Here's what I want it to be. What can I do to get it there? Or I don't want it up there, I want it down here. Depending upon I want something, that variable to have a different outcome, what do I need to do to change in my causal contextual environment to produce the outcome I want? That's a prescription. Okay, so again, predictive analytics, given X, find Y. Prescriptive analytics, given Y, find X. Now, I've had a few decades of mathematics, several semesters of calculus to get to a physics degree. You don't need all that to realize that given X, find Y, and given Y, find X are really sort of opposite mathematical statements, okay? They really are opposite things. But they all derive from finding those correlations in your data, especially when you have the higher dimensions. And so what you're really discovering is how that system behaves under different circumstances. How does it evolve? How does it respond? What does it look like? That's called the object's DNA. So all that data is giving you the object's DNA. Okay, so that's 2. Number 3 is outlier detection. It sort of speaks for itself, except it doesn't, because my friend who put together this banana diagram did something really clever. Can you see from your seat in the middle of Data Cloud 2, the lower section of Data Cloud 2, there's a little blue-shaped, sort of heart-shaped thing there? Can you see that? The lower port of Data Cloud 2, there's a little blue smudge there, sort of heart-shaped, kidney-shaped. That was intentional. That's not a smudge on the screen. That was intentional. That's meant to represent a void. It's a region that the data avoids that region. Now, in astronomy, we have lots of examples like that. And when we find those things, it tells us there's some physical law, there's some astrophysical reason why that thing in nature doesn't want to be in that spot. And so when you discover those voids, it's an aha moment. It's a discovery moment. They said, what is it about the system that's telling me that it can never be there? Okay, so an outlier can sometimes be right smack dab in the middle of your data set, and yet it shouldn't be there. That's an inlier. And it's just as interesting and surprising and anomalous and novel as the outlier who's sitting 7 standard deviations from the mean. So an inlier can be 0 standard deviations from the mean and still be extremely interesting discovery. So surprise discovery, number 3. And then when we get to number 4 here, it's the 4th one, deserves its own little cartoon of its own down at the bottom left there, and that's link discovery, network analysis. Okay, discovering interesting associations in links, just like the product recommender engines, or even like marketing attribution, or fraud detection, because it's not A communicates to C, but A communicates to C through B. Okay, so marketing attribution is just like that. Illicit money transfers is just like that. It goes A to B, B to C, because if it was A to C, someone would notice and they would get arrested. Okay, so it's the hops in the graph and the dots that are not connected directly, but transitively through other nodes in the graph. That's where the real discovery happens. So associated and link discovery is another great way of discovering value in your data. Okay, so all those different ways of discovery can be applied at different levels of analytics maturity. Okay, so these levels listed here are, in a sense, orthogonal to the things on the previous slide. That is, you can do all the things on the previous slide in some way or another at each of these different levels here. So there are different ways of describing what we're doing. So the analytics are the outputs, the outcomes, the delivered value from all the stuff we're doing, all the data science we're doing, all the discovery we're doing from our data. So what are some of those things? Well, number one is descriptive analytics. You can produce a report and say what happened. All right, now that may seem kind of boring because it's a historical hindsight what happened type of thing. But if you're in a publicly traded company, which I am and Oracle is, you know you have to do quarterly business reports for Wall Street. It's required by law. So descriptive reports are invaluable and keep you out of jail. Okay? So even though it might be at the lowest rung in this maturity ladder, it's still absolutely essential in some settings. So what you're doing in descriptive analytics is you're answering the prescribed questions. You're answering the questions given to you. You'll see when we get to number 5 here, I'll sort of jump to the gun here. Number 1, you're answering the prescribed questions. And number 5, in cognitive analytics, you're discovering the questions you should be asking. That's the fully human cognitive role or analogy for analytics, which is you look at your data and say, why is that happening? Why is that outlier there? Why is there this void here? Why is this trend suddenly changing slope? Why did this change under this condition, but it didn't change there? What is this new emerging subcluster in my medical data or in my customer data? All those questions, don't avoid them. Embrace them. And sometimes the question may come from the most junior person on your staff, and it may even come from a family member because you're preparing your presentation for the Oracle Code 1 stage, and you show it to your family before you leave home, and this youngest member of the family who's 6 years old said, "What's that?" My grandkids call me Poppy. "What's that, Poppy?" Well, that didn't actually happen, but it did happen years ago when my kids were that age. Okay, so let anybody look at your data, because they will see things that maybe you didn't see. So cognitive analytics is that highest level. Now find me the questions you should be asking from your data. But along the way, we're doing these things, and I give them these funny words: hindsight, oversight, foresight, insight, and then finally I had to come up with something that rhymes with sight, so right sight. Okay. So hindsight, that's descriptive. Diagnostics is oversight. That's sort of real-time analytics, what's happening right now. Predictive analytics, we already talked about what will happen. That's foresight, sort of seeing the future. Forecasting. Prescriptive analytics, that comes from the insight we talked about. Given all these other data sources and these other dimensions of the data, we have insight into how our system behaves in ways we never saw before because we have all this contextual data now. So insight discovery enables us to prescribe better outcomes, how to optimize outcomes, choose the next best action, make the next best decision given our data. So that's prescriptive analytics. And then cognitive analytics is, again, having that full view of things where you say, what is it that I should be doing? What is the question I should be asking? What is the right thing to do right now in this context at this point? So cognitive analytics moves beyond just answering the given questions, but generating new questions from your data. So those are the things we do with our data. So we produce value by applying algorithms to data, discovering patterns, and building models from them. So that's taking us through machine learning and data science, actionalizing it, which might be the AI, and then the products of those things are the analytics. So all that terminology is defined here on the screen. There's a couple of things besides the busy definitions there that I want to call your attention to. First, the very top 2 lines of the slide, it says, learning is an iterative process, right? You learn fast, fail fast to learn fast, we know that, right? The best way to learn something is to make mistakes and learn from it, learn from your mistakes. So learning is an iterative process. Science is an iterative process. So scientists develop hypotheses, they test them, and they do experiments to test them, and sometimes it doesn't work so well, so you refine the hypothesis and you try again. So it's an iterative process. So if learning and science are both iterative processes, it's not too surprising that machine learning and data science ought to be iterative processes also. So machine learning are these algorithms that learn through that process of failing, that learns from experience, just like a child learns from experience, right? So the best line I ever heard that describes machine learning also applies to raising teenagers, right? Good judgment comes from experience, and experience comes from bad judgment. So when you build a model, you build a rough model, and of course it's going to be wrong. And we have things like gradient descent and backpropagation and all these cool techniques in machine learning that feed the error information back to the model to adjust it to make it better. It's algorithms that learn from experience. Just mathematics is all it is. Data mining is how we apply that to data to do discovery. AI is how we apply that data to taking actions. Data science, then, is the scientific methodology that we apply to do all that, all the different pieces of science, hypothesis generation, experimentation, data collection, validation, refinement, all those things. That's the process, that's the methodology where we use the math to build models that we test to deploy, and then when we deploy it, we actually then have the analytics. That's a deployed thing. And so the second quote I wanted to draw your attention to, besides all the definitions in the top line, was the thing in the yellow box on the right. That is the two most important things in data science. So if you remember anything else today before you leave and after you leave, the two most important things in data science are the data and the science. Because the data are the raw objective truth, the raw objective reality, the fuel for our models, and science is the methodology by which we hopefully don't trap ourselves into confirmation bias. Oh, that model worked. Test it, verify it, put it through some paces, try it on a different data set, see if it generalizes. Don't get stuck in a bias trap. It's an iterative process, and it's okay to be wrong first. Okay, so Thomas Edison, someone complained to Thomas Edison, that he failed 1,000 times to invent the light bulb. And he said, I didn't fail 1,000 times. I learned 1,000 ways not to build a light bulb. Okay, so failing fast to learn fast is an adoptable good practice in business. So analytics by design basically goes back to my last point at the very bottom of that last slide, which is analytics are the products. We need to focus on our business outcomes, our goals, our objectives. What is your mission? What is your North Star of your business? That should be determining what you do, where you go, and how you go there. All right, some people say they're data-first organizations. I'm not going to complain if that's a way you want to describe it, but I don't like using that phrase because every organization has data now. That doesn't distinguish you from anybody. Just like years ago, people would brag about how big their data sets were. And that doesn't separate you, make you distinguishable in the marketplace. What distinguishes you are your output, your products, the delivered value from your data. That's the analytics. So focus on what it is we want to accomplish. What are our business questions? And that's a good science practice too. Good science starts with asking a question, a hypothesis. What am I looking for? An hypothesis that explains this thing that I see. Okay, test it, verify it, go through a process. So analytics first is good business strategy. It focuses on outcomes which matter, and also it focuses on products, which are the value that we create from our data. And as you build products that are increasingly successful, and it may start with some very, very small things like a very simple recommender engine or a very simple chatbot that very simply is plugged into your customer service call center and answers the FAQs for people. Because like 80% of the questions that people call for call centers are just in the FAQs, which are already posted on your website. But people don't read anymore, so they call the call center. Call center people are frustrated because it's the same old questions, and it's right there on the website, people. So you can actually have an API, call a chatbot, feed it your FAQs, and you're done. No coding, no work involved, basically. And you've just solved 80% of your customer service calls. But not only that, you've made your employees really happy. Because the last thing an employee likes to do is answer the same question over and over and over and over and over again. So you're improving employee experience, which therefore translates into better customer experience. Happy employee, happy customer. You see the equation there, right? Okay, so by focusing on those small victories, then you encourage the culture to accept larger projects around AI and machine learning. Because there's a lot of fear in the marketplace and in businesses and companies and organizations everywhere. People fear job loss. But at every tier of the organization, people think, someone's going to do my work, or someone's going to do my decision making, or someone's going to run the company. So everyone thinks that they're not going to have a place anymore. And that's true. The jobs will change, but we'll need more people for the new jobs. So let's deliver value, and that'll inspire the culture change that'll lead us to those bigger implementations. So at the end of the day, this analytics by design means think about the products we want to deliver that are going to deliver the value, and there's some there at the bottom of the slide there. I ran out of room. I got the ... there because I put the word models in my original slide about 7 times in this place, because the models really, to me, are the key thing. It's the models of how customers behave, how your systems behave, how your website behaves, how your database behaves, how anything behaves, right? So those models become sort of the fuel, the engine that is driven by the fuel, which is the data, which leads to the output, which are the analytic products. So what's going on in that engine? What's going on in this machine learning engine? We talked about algorithms that learn from experience. Okay, that sounds pretty damn vague, really. What does that mean? Well, again, they learn from patterns and data what something will do or how something will behave. So just like I always say, like the first caveman comes out of the cave and they see this animal in front of them, they have to, first of all, they have to do object recognition. They recognize it's an animal and not a bush. Okay. Okay, so there's object recognition. Okay, so pattern recognition, or pattern detection, I should say, pattern detection. Then they do recognition. They have to recognize, is this something going to eat me for lunch or can I eat it for lunch? So either way, if you make the wrong decision, your day's over. Okay, your life's over. Okay, so it's clear that we need to learn from experience. And so supervised learning is given the training data, given past data, labeled data, how can we get an algorithm that can detect, for example, a cancer or a failing engine or a cancer patient or an unhappy customer or whatever. Okay, so we learn from feedback, from labeled data, from prior experience, historical data, training data, and build the model so we can deliver a better outcome, and that's called supervised learning. It's given past experience, we know how to deliver better. Then there's this thing called unsupervised learning, where you basically say, what patterns do I see in the data, independent of what my biases might be about what I'm looking for? Okay, so I might see these new clusters emerging, these new patterns emerging, these new trends, these outliers, these inliers, these new links in the graph, the social graph, the product graph, the knowledge graph. All right, it's unsupervised, it's data-driven. Okay, it's finding things in the data in a sense that the 6-year-old can find. All right, what's that? Why is this? All right, asking those questions, finding that hidden structure that you didn't previously know about, unsupervised learning. So it doesn't necessarily require labels, okay? So you're looking at a radiological image to see if a patient has cancer and there's some funny little smudge over here on the lung. Well, would you like for your doctor to ignore that and say, okay, you don't have cancer, bye. You should have paid attention to this thing over here, okay? Because that might be something serious. Okay, so the third kind of machine learning is reinforcement learning, and that's how the machines learn how to play chess and Go and beat the world champions. Okay, they play the game with a reward stated. What's the reward? You know, what's this? How well am I doing? There's a score. There's feedback, and that reward process trains the machine how to do better. It says, okay, if I do this, I get worse, or if I do that, I get better. So that reinforcement learning is a very significant iterative process. Okay, and that's really powerful for decision-making in autonomous systems because it's learning rapidly, from its experience. So traditional programming, this is oversimplification. Don't get in an argument with me about this because it's not my slide, but I actually do believe this slide. So traditional programming, right, is you write a program and you give it some input and it generates an output. That's sort of what I did back in my high school days. I had these positions of the planets on the sky. I put it in a program and I could generate those numbers. I was amazed I could generate the predicted positions of the moons and the planets just from what I was doing right there. Traditional programming like that. So supervised machine learning, I'm going to emphasize supervised because that's what specifically in this case. We have the data, we have the input data, we have the labels, that is, these images represent patients who have cancer, these images represents patients who don't, or this time series represents an engine that has normal behavior, this represents an engine that has a malfunction that's about to happen or will happen soon. This data predicts happy customer, this data predicts unhappy customer. Think about sentiment analysis, right? So we have data and we have output. We know what the outcome will be. Then we find the model, we find the program that reproduces the data in the output. Okay, so what we're looking for is the program, the model that will generate from the input the desired output. Then we apply that to our new data. Okay, so the top level of this plot where you see the blue arrows, we have training data coming in. We extract interesting features from the data to generate a model, an algorithm from machine learning, whether it's class discovery, correlation discovery, novelty discovery, link discovery, whichever we're doing. And we build a model that can produce correctly those outputs. We correctly label a cancer image, correctly label an unhappy customer, correctly label an engine that's malfunctioning. Then, once you have that output, again, the output is the program, then you can apply that program to new data. So then you get sort of to the more traditional input, program, output. Okay, you feed the new data through the model and generate the output. That is, you predict the class variable, cancer, no cancer, engine fail, not fail, happy customer, unhappy, whatever. All right, so you apply the model, that's where the green arrows are. But remember this famous quote from the statistician that all models are wrong, but some are useful. So don't get stuck with analysis paralysis saying, well, this is not entirely correct. Remember the 80-20 rule, right? I mean, 80% of the value comes from the first 20% of effort. Okay, so you can get that 80% of value in your first 20% of effort. Sometimes you don't need to spend all that extra effort, 5 times more effort, just to get the last 20%. All right, all models are wrong, but some are useful. Sometimes the simplest models are the best, and I can tell stories about those, which I don't have time to do today. Anyway, so in this rapidly expanding frontier, there's some examples which follow. There's a link to the slides at the end where you can read all these things in gory detail. I don't have the time this afternoon to read through all these for you. But machine learning, okay, so there's like 9 or 10 things from that previous slide that I'm going to just fly through here. So machine learning algorithms that learn from experience, for example, recommender engines, digit detection at the post office so it can read the zip code on your letters, spam email detection, cancer detection. I talked about those. So these are algorithms that are trained from historical data to learn how to label things correctly, models that can learn how to get things right. So AI, that actionable intelligence, that accelerated, augmented, assisted intelligence, augmenting the human in the loop, nothing artificial about that, bringing data to action, those applications. Well, the first 4 are the ones that were just on the previous slide. The algorithms and models that we learn, that's just mathematics and coding. Now we apply it, that's the AI. So those first 4, 1 through 4, my examples, as it says there, examples 1 through 4 are the applications you just saw. Other examples include credit card fraud alert and conversational AIs, the Siri, Alexa, chatbots, and so on. Robotics, we know about that. Okay, so robots respond to sensory inputs to move through their environments. That's a data input, decision output, action output, based upon data. 3D printing. Now this may seem kind of boring because 3D printing, you sort of have to build a model of the thing, and then you feed the model into the printer and it prints it out. That's called additive manufacturing. It may not seem too interesting, but 4D printing is really the wave that's coming, where the system can, for example, using carbon nanotubes, it can actually respond to sensory input and change shape in real time. So medical doctors are using carbon nanotube heart stents that they implant into patients with a sensor, a heart monitor, blood pressure, and various sensors in the body. And when that patient is going through some stressful moment or has a sudden heart fibrillation or higher blood pressure or body temperature change or something, the shape of the heart stent will change in real time in their body in response to those sensory inputs. That's 4D printing. It's changing in space and time in response to input data in the body without further surgery. That's insane. There's a YouTube, you can read about this. All right, virtual reality. Again, it's a virtual environment, but a lot of times there's sensory inputs and sensory motions that make the reality experience real because it's actually detecting all that from sensors. Augmented reality is when you now have data superimposed on the real world. So whether you're in the shopping mall and you say, where are the sales? or I go into the grocery store, where are the Cheerios? Okay, so I could have that augmented reality right there on my phone. So it shows me my store with labels on it. Or it might be in disaster response, showing where there's down power lines or patients or people in most distress, okay? Or other kinds of things. Or there's augmented reality of this app where you actually can stand in front of a mirror in a store, try on a new outfit without trying it on. Stay in your own clothes, select the clothes you want to see how you look in it, and it just shows you in the mirror with those clothes on without you actually having changed anything. Okay, pretty amazing. Okay, IoT, I already talked about that. It's data everywhere, generating fuel from these sensors to all kinds of things. Autonomous vehicles, we don't need to talk about that at length. We know about that. Obviously, sensory inputs, driving actions, literally. Drones, similar sort of thing. Sensory detection, whether it's for disaster response, military applications, or construction sites, or just for fun, or whatever, sensory data analyzed by algorithms to say what's going on. All these things are examples of dynamic, data-driven application systems, okay? So all these things are doing measurement from sensors of all kinds. It's doing inference that is building a model of how I think this thing is behaving, building a prediction to say, if I do this, this will happen, or this is likely to happen. So it's both predictive and prescriptive, actually. And then the last part is this S called the steering. That is the actual action taking. An autonomous system who now takes an action based upon this chain of events. I measure something from sensors everywhere. I infer something from it. I make a decision. Okay, so decision is really a prescriptive analytic process. If I decide to do this, this might happen. If I decide to do that, that might happen. That's what happens in boardrooms every day. It's a prescriptive discussion. If we do this, what will happen? If we do that, what will happen? So you go through that process, that inference from your data, data-driven. That's why this slide is about dynamic, data-driven systems. Then you can have an autonomous system anywhere in the world, including in your database. Which brings us to the autonomous database at Oracle. But I talked to NASA folks for years, long before anyone had a vision of autonomous databases, of how can we use AI, or how can we use data science for data science? Using data science to label data. Use AI to create tags, semantics, taxonomies, descriptions, indices, organizations of our data. Imagine a library. Imagine walking into a library. People remember what libraries were? Yeah, sort of. Mostly people with gray hair. Anyway, so you go to a library. The books are organized alphabetically by the third letter of their middle name, right? No, they're organized by the Dewey Decimal System, so you know how to find something. There's a system. They're indexed in a certain way. But imagine if you walked in that library and the index suddenly changed based upon your preferences and your interests and the things that you like. And suddenly it's all organized according to your personal preference. Your personal interests. Suppose I like cooking in the mountains, so I want some outdoors books next to some cooking books. But I want to do it under the stars. I'm an astronomer, so I want it next to the astronomy books. Okay, so the whole system organizes the data and presents it to me based upon my digital breadcrumbs, things that I have already done with data. How have I used the data? How have I found interesting things in the data? Even digital breadcrumbs that can identify friction points where the person constantly keeps trying and then doesn't have success. You can detect that in the data. So adding data to data, using data science for data science to make our data systems more useful for the data applications we've talked about. So truly, it's a data world after all. Data really helps our world go around. And let's not forget what Larry Ellison said, that our mission is to help people see data in new ways, discover insights, and unlock these endless possibilities. So thank you very much. Come for the data, stay for the science.
All right, that was great. So we're going to talk a little bit now about how you start to take some of these concepts around data science and machine learning and turn them into applications. Okay? So right now we've got this phenomenon really where there's been an explosion of technologies for developers. There's languages, there's frameworks, there's platforms. In some ways, it's really fueled the availability for developers to be more productive than ever. Some of this is being built by developers themselves via open source. But the ability to solve problems quickly and correctly has moved up exponentially over the years. And why is this, right? So in a sense, it's always been easy for developers to cut code. And technology is something you can learn, right, and apply. I think what's changed now is that there's a possibility of architecting a new generation of end-to-end solutions very quickly. You can prototype them in real time. You can upgrade these projects toward production very quickly. And one of the major factors that has opened this up is really the emergence of reliable and stable public cloud platforms, right? You don't have to go to data centers and rack and stack machines. Your compute, your storage, your data management, it's there, it's available on demand. So now you can get to where you have complex solutions and the infrastructure to run them really within minutes, right? So that means the barrier to adopting new technology has gone down quite a bit. The cloud's now opening up a new paradigm, a new type of application as well. And we're going to talk about that today and tie it back into some of these topics around data science and machine learning, right? So we see this emergence of what we're calling an intelligent cloud native application. And we mean intelligent because it typically involves the embedding of machine learning models directly within the applications themselves. And this has a lot of implications for how to think about apps. For one thing, it means that data takes on a new kind of centrality, and developers have to start thinking differently about data and about data management. Right? So applications are no longer about CRUD operations over top of a database. There's different scale of data management, different kinds of data management systems. And more importantly, when you have machine learning models, you have to think about the data differently. In many cases, the knowledge is embedded inside the data, but even the developers themselves that are utilizing the model may not really understand fully what that knowledge is. So we'll try and unpack that a little bit here. But to do it right and to make it maintainable, and to ensure that the machine learning models stay correct, stay consistent as data itself starts to change and drive appropriate decisions over time, applications really need to be cloud native, and we'll try to show you why today. So let's talk a little bit about modern applications and the evolution around application development that's gone on over the years, right? A lot of times now we talk about apps, we talk about services being born in the cloud. And this is the end of a long process. So way back in the 80s, going into the mid-90s, data centers were built with physical servers, apps were very monolithic, the way teams work was very much the traditional waterfall style. As we move forward in time, and we get into the late 90s, in the early 2000s, a lot started to change, right? Here we had the emergence of virtualization. Right? You saw probably some of the announcements around VMware on Oracle Cloud today. A lot of virtualization technologies opened up and made things more flexible. We also had N-tier applications. This was the heyday of the application server, the JEE standards and so forth. So people started to think about applications being very much multi-tier and not monoliths. Data centers were starting to provide hosting and converting over to using Linux servers, commodity hardware. So the cost overall of deployments was going down. And then we had the emergence of Agile methodologies, right? And this was back, if you look at this period when extreme programming books were out, they were almost like, I remember going through each of these books in the extreme programming series, and they were almost like religious texts at the time, because it was so different than the way people had thought about waterfall applications. So, so somebody else remembers too. So then we get to today, okay? And this evolution continues to change, but it's building on these foundations, right? So now we're seeing containers replacing virtualization, easy to have, very fast and agile deployments. Apps are often designed as loosely coupled microservices, and DevOps has become very much a standard thing. Continuous integration, continuous deployment. It's very much the way of the world these days. So this move to cloud-native applications has been really about fast and reliable application development. And it sits on this lineage, and it's been proving itself out to be very effective. So when you go and you think about how you build a modern app, right, the agility is one of the key factors. The ability for deployments, for operations, and for the evolution of the application itself to move quickly and move reliably, move correctly. So typical workflow, let's just kind of walk through this image a little bit. Teams, they're going to write code. They're not necessarily bound to a particular tool or particular development language. Teams can select the DevOps environment that they want to set up their development pipelines around. Once you get the code built, compiled, you can package it up, put the libraries and binaries together into a container. So now you have this unit that's executable, it's very portable, it's very fast for deployment. Push the image into a container registry, and you're ready to go. You can use Kubernetes, popular open source framework, to stage the containers into a cluster, and you can start to run your application or your microservices. So oftentimes you'll have a series of microservices that are bootstrapped, where each container is kind of serving a specific set of functions within the overall application. You can spin them up and down very quickly, especially compared to a virtual machine or traditional binaries thrown onto an OS on bare metal, right? So each microservice tends to be independent of the others. You have more flexibility, but you have more resilience within the application architecture overall. When it's time to upgrade a microservice, or when you're doing bug fixes and patches, it's typically replaced directly, right? No more patching systems. You're really making changes in place, just replacing containers, moving forward with your testing, and upgrading your application in real time. So each of these things, each of these microservices themselves may be responsible for managing data, right? That's typically, often at least, in a database. It can get challenging when there's a lot of different microservices together and a lot of different databases, and you're trying to get these things to work collaboratively and not have bottlenecks. So one of our speakers, Maria, who will be coming up, will talk to that a little bit. But this model requires, it's effective, it works, it's flexible, it makes it easier to have rapid progress, rapid evolution. It also has an overhead from an operational perspective, because now you've got lots of little services, lots of little servers running. And I think cloud platforms are getting smarter about this as well. So this is where we're starting to see the emergence of models where you can take the container and deploy it into a serverless architecture. So you can get the best of the design characteristics of the microservice model on the one hand. On the other hand, we can reduce or eliminate the complexity of operating the system. So the idea with a serverless model, something like what we offer in Oracle Cloud Infrastructure, our function service, which is based on the open source FN project, the idea here is that when a request comes in for the service, the code is instantiated, it executes, it completes the work, and then it can shut down. So you're really only paying for what you're using, and you're not really responsible for running the back-end infrastructure. That falls on the cloud vendor. So it's a kind of a cool way that the cloud platforms are getting smarter about helping modern applications move fast. Now, that touches on maybe some of the typical approaches to designing a macro architecture for an application. But what about this idea of intelligence, right? Here we see that there's a new breed of modern applications that's emerged, and they're using machine learning to drive the decisions within the app itself. And what's cool about this is that oftentimes you're moving away from static rule-based systems, you're getting better outcomes, and you're really able to drive business decisions that are derived directly from the data that the business has, right? So a lot of this today is very real, right? It's emerged as a pattern we're seeing now repeatedly, almost typically, as we're talking across projects with development teams, many different kinds of enterprises. I have a few examples here. So one that I like quite a bit is medical diagnosis. I did a general session yesterday on AI and artificial intelligence where we demoed an application where you fed it X-rays, chest X-rays, and the system learned to identify pneumonia. Now, what's cool about this kind of system, and Dr. Borne had talked about cancer identification, is that oftentimes the machine learning models can do a better job than radiologists, a better job than humans, right? So that doesn't necessarily mean the humans don't have a role, or you don't want humans checkpointing things, but there's a lot of power in this. Another neat example, smart agriculture. We've got guests here at AgroScout, which is an Israeli startup. Here at Code One, they're doing a session. They've developed an application where they have low-cost commercial drones that generate images of crop structures, and they can detect pest infestations, they can detect diseases all the way down to the level of individual plants. And it's much more cost-effective than doing it with satellites or trying to do it with airplanes. So it's a really cool example of a high-value AI-driven application that in some ways impacts us all, right? We're all consumers of agricultural products. Oracle itself, internally, our SaaS applications, we're using machine learning all over the place. So in Oracle Cloud, we have an offering called the Oracle Hcm Cloud, and it uses machine learning models to sift through resumes and match them with best fit job openings, right? There are machine learning models that are used to help customize career progression for employees within the application environment. Similarly, within the Oracle Customer Experience Cloud, we use machine learning to recommend best offers for salespeople, right? Finding not only what is the fit for the product from the data we have about the customer, or the data that you have about the customer, but also how do you optimize around the pricing that is going to make you get a deal where it's a fair exchange of value on both sides, right? So these are great examples of how machine learning is already showing up in custom applications, in commercial applications. So the question really is, how does this impact your app? How do you go about doing it, right? And it's an interesting problem because the centrality of data and the importance of having a cloud platform really become clear when you look at the full life cycle of a machine learning model. What happens when you're going to engage application developers and data scientists together to create solutions based on artificial intelligence. So first, data scientists have to be able to find the data, explore it, understand it, right? Key thing, actually, for a lot of organizations, just getting the data is a challenge. Once they have the data, they got to be able to work with it. And one of the main tasks in a data scientist's life is what's called feature engineering. And this is where you're selecting the right data sets, you're working to scale it, you're forming the data, you're combining it, limiting to subsets, et cetera, in such a way that it's optimized for feeding into the algorithms that are going to be used to build the machine learning models. So feature engineering's key task, turns out it's hard, right? Because you want to get an optimal model, and it's sensitive to the kinds of data and to the tuning of the model, et cetera. On a data science platform, like what we have in Oracle Cloud, we actually use machine learning to help make those tasks easier. We automate a bunch of the feature engineering work, and we call this AutoML characteristic of the platform. And now, once you get the model, you start to figure out what your data sets are, and you start to optimize the data for the models. You have to do the training. It's not a one-time event, right? Training often requires specialized hardware. You want that hardware to be available on demand. We've seen a number of examples where there are very large data sets, and users are training models with CPUs. It's taken them weeks and weeks to produce a model. They've switched over to GPUs, which are much more efficient. They're built to do matrix math, and they're able to build the same model in hours, right? GPUs are expensive, so having a platform where these are available on demand, where you can get these workloads processed and turned around quickly, is another key part of a platform that you want to have available. So third, the next area, once you've built a model, they need to be easily deployed. And it turns out this is another surprisingly difficult problem as well. Lots of times organizations are struggling where they're trying to get the model that data scientists have created on their platform into production. They're bringing in engineers. They're trying to re-implement the algorithms, re-implement the models. It's tedious. It's error-prone. It leaves aside security and governance concerns. So you want a platform that takes all this into account. It makes it easy to operationalize the model so it can be embedded inside the application. That's an important step, obviously. But once you have the model is only as good as the data. And invariably, data changes over time. So think about this. If you built a predictive model for a stock market investment, and you built that model in 2006 or 2007, we had the real estate market debt crisis in 2008. If you were using the model after the crisis, it's going to give you very bad results, right? It's going to be basically useless. So you have to have a platform beneath the application that's making sure that the models remain predictive, that the predictions are effective, that as the data changes and the predictive efficacy of the model declines, you can retrain the model, you can redeploy the model, and you can automate this process. So the best part, in our opinion, the best place to do this by far is a cloud platform that's designed to manage machine learning models, right? So that's an important part of the modern data architecture, the substrate for machine learning that underlies or is a companion to the modern application architectures that have emerged over the years. So we at Oracle, what I'm going to show you here is a kind of a snapshot in the large of Oracle's second generation cloud infrastructure, OCI. Okay, it provides bare metal compute, virtualization, and containerized compute. Importantly, it's got things like GPUs on demand for performance-intensive workloads like machine learning. Right? So the platform is built from the ground up to do HPC and data science type workloads at that basic infrastructure level. We also have a whole array of services for developers to use to build these modern applications. You have a choice of programming languages and frameworks. You can use Java, JavaScript, Node.js, Python, Ruby, et cetera. You're not locked into any platform in particular. We have tools for developers and DevOps. We have free tools like Developer Cloud, but you can use whatever you're already familiar with and run on the platform. And we also have low-code platforms, something we call Visual Builder, which lets you do very simple, little to no code deployments for modern apps. okay? Above that, we have a set of cloud-native services which are based on open source. It includes managed Kubernetes, again, a part of this typical modern app deployment architecture, and a container registry. We've got things like managed Terraform, so you can do easy spin-up of libraries and applications that you've designed, or third-party software components. And we have a fully serverless infrastructure called Oracle Functions Cloud Service. It's based on the open source FN project. We also have a fully integrated data platform. Now, this being Oracle, as you'd expect, we have our flagship autonomous database, right? But we also offer a whole range of database, open source databases like MySQL, third-party databases like we've started to support Microsoft SQL Server, NoSQL options, et cetera. All there is an integrated part of the platform. We have a serverless Apache Spark service that we call Dataflow that lets you do big data operations at scale, which can be particularly important for some of these intelligent applications where you're working on training models over very large data sets. We have an Apache Hadoop service, and data integration services for bringing data in, transforming it, doing data prep, which can be a precondition for the data science projects. All this can be managed in a data catalog. All these data assets can be tracked across the cloud, and all these data management systems, so you have an integrated view of the data assets that are in the system, who owns them, where they came from, et cetera. And then one level above that, for artificial intelligence, we have a rich set of services to make it very easy to build things like chatbots and digital assistants, to create machine learning models, and to build blockchain solutions. You can embed these machine learning models directly into your app using our data science cloud service. So it's all there as a complete platform. We think it's really the best offering in the market today to build these modern, intelligent, cloud-native applications. So we did this, we built this, and we designed it with 4 central principles in mind: open, modern, easy, and intelligent. Okay? So what do I mean by this? We're open in the sense that we don't lock you in. We use open source all over the place. We make open services. We generate a lot of our services based on open source capabilities that we're optimizing for the cloud environment. And we allow you to bring any kind of application development tool or platform into the cloud. There's a whole range of data management capabilities, so openness is key. We also have been focused very much on modern applications, right? Especially when it comes to modern architectures, modern deployment choices, and allowing you to take advantage of the serverless paradigm. And we're going to see some examples of that coming up. The Oracle Cloud makes it easy to get started in minutes. Easy to sign up. There's now a free tier for developers. You can get started today, right off the bat, and start using everything I'm talking about right here. And of course, we have a big focus on building intelligent apps. Apps that are powered by machine learning, that have advanced analytic capabilities. The platform itself, as I said, is optimized for HPC workloads. It's optimized for data science. And we have services like our data science offering that make it easy for teams of data scientists to work collaboratively, get their models into application consumable forms as APIs, and then manage those applications through the whole life cycle, where it may involve continuous retraining, redeployment as the data sets change and shift. So we definitely are proud of what we're offering.